Welcome to the lecture presentation for Chapter 3 on Matter and Energy from Introductory Chemistry. Everything you see is made of matter. Different kinds of matter are related to the differences between the molecules and atoms that compose them. The image shows water molecules on the left and carbon atoms in graphite on the right. Matter is anything that occupies space and has mass. Some matter, like steel or water, is easily visible. Other matter, like air or microscopic dust, requires magnification to see. Matter is ultimately composed of atoms, which are submicroscopic particles. Atoms bond together to form molecules in specific geometric arrangements. Advances in microscopy allow us to image these atoms and molecules. All matter is composed of atoms. In some substances, such as aluminum, the atoms exist as independent particles. In other substances, like rubbing alcohol, several atoms bond together in well-defined structures called molecules. A scanning tunneling microscope, or STM, creates an image by scanning a surface with an atomic-sized tip. This image shows nickel atoms as blue bumps. This is another STM image, showing a DNA molecule. DNA is the hereditary material in living organisms. The double-stranded structure of DNA is visible in yellow. Matter can be classified into three common states: solid, liquid, and gas. Water is a good example, existing as ice, liquid water, and steam. This diagram illustrates the three states of water at the molecular level. Molecules in a solid are closely packed. In a liquid, they are close but move freely, and in a gas, they are separated by large distances. In solid matter, atoms or molecules are packed close together in fixed locations. Solids have a fixed volume and rigid shape. Examples include ice, diamond, quartz, and iron. There are two types of solids. Crystalline solids have atoms or molecules arranged in repeating geometric patterns. Amorphous solids lack this long-range order. Examples of crystalline solids are salt and diamond, while amorphous solids include glass and plastic. The images show the difference. A crystalline solid has a well-ordered three-dimensional structure, and B, an amorphous solid does not have any long-range order. Sodium chloride, or salt, is a prime example of a crystalline solid. Its well-ordered cubic shape reflects the well-ordered cubic arrangement of its atoms. In liquid matter, atoms or molecules are close but are free to move past one another. Liquids have a fixed volume and assume the shape of their container. Water, gasoline, and alcohol are examples of liquid matter. In gaseous matter, atoms or molecules are separated by large distances and are free to move relative to one another. Gases are compressible and always assume the shape and volume of their containers. Examples include oxygen and helium. This image illustrates the compressibility of gases compared to solids. Because gas molecules are not in contact, they can be compressed, while solids are not compressible. This table summarizes the properties of solids, liquids, and gases, contrasting their atomic motion, spacing, shape, volume, and compressibility. Matter can also be classified by its composition. A pure substance is composed of only one type of atom or molecule. A mixture is composed of two or more different types of atoms or molecules combined in variable proportions. An element is a pure substance that cannot be broken down into simpler substances by chemical transformation. All known elements are listed in the periodic table. Helium is an example of a pure element, composed only of helium atoms. This image shows a balloon filled with helium. A compound is a pure substance composed of two or more elements in fixed, definite proportions. Compounds are more common than pure elements and can be decomposed into simpler substances. Water is a compound, composed only of water molecules with two elements in fixed, definite proportions. A compound is a pure substance with different atoms chemically united in fixed proportions. A mixture is different substances that are not chemically united, but simply mixed together. Air and seawater are common examples of mixtures. Air is a mixture of gases like nitrogen and oxygen, and seawater is a mixture of salt and water. A pure substance can be an element or a compound. A mixture can be homogeneous, like sweetened tea, or heterogeneous, such as oil and water. This flowchart summarizes the classification of matter, distinguishing between pure substances and mixtures, and their subcategories: elements, compounds, homogeneous, and heterogeneous mixtures. To summarize, matter can be a pure substance, which is either an element or a compound. Matter can also be a mixture, which is either homogeneous or heterogeneous. Mixtures can contain elements, compounds, or both. Matter also has different properties. A physical property is displayed without changing the substance's composition. A chemical property is displayed only when the substance's composition changes. The odor of gasoline is a physical property, as its composition does not change. The flammability of gasoline is a chemical property, as it changes composition when it burns. Let's explore the physical change of water. The atomic or molecular composition of a substance does not change when displaying its physical properties. When water boils at 100 degrees Celsius, it changes from a liquid to a gas, but it is still water. Boiling is a physical change. When water boils, it turns into steam, a gas, but the water molecules remain the same in both the liquid water and the gaseous steam. Changes of state, such as from solid to liquid, are always physical changes because the fundamental composition of the matter does not change. In a physical change, matter changes appearance but not composition, like ice melting into water. In a chemical change, matter does change its composition, such as copper reacting with air to form new compounds. An example of a chemical property is the susceptibility of iron to rusting. Rusting is a chemical change where iron turns into iron oxide, a completely new substance. Matter undergoes a chemical change during a chemical reaction. Substances present before the change are reactants, and those present after are products. Physical changes do not alter the fundamental associations of atoms, resulting in a different form of the same substance. Chemical changes alter these associations, resulting in a completely new substance. Vaporization, like liquid butane turning into gaseous butane in a lighter, is a physical change. The molecules remain butane, only the state of matter changes. Burning, however, is a chemical change. When butane burns, it reacts with oxygen to form new molecules, carbon dioxide and water. Distillation is a method for separating mixtures. It uses physical changes, like boiling and condensation, to separate components based on their different boiling points. Filtration is another technique to separate mixtures, using a physical barrier to separate a solid from a liquid or gas. The law of conservation of mass states that matter is neither created nor destroyed in a chemical reaction. The total amount of matter remains constant during physical and chemical changes. In the example of burning butane, the total mass of the reactants, 58 grams of butane plus 208 grams of oxygen, equals the total mass of the products, 176 grams of carbon dioxide plus 90 grams of water. The behavior of matter is driven by energy. Energy is the capacity to do work, which is defined as the result of a force acting over a distance. Understanding energy is critical to understanding chemistry. The law of conservation of energy states that energy is neither created nor destroyed. The total amount of energy is constant, although it can be changed from one form to another or transferred between objects.